All right, well, welcome everyone to our weekly Wednesday webinar series, Practically Perfect Plumbing Part 2. This is a follow-up to a session we've already done with some more information and more things that we're always learning. This course is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I'll be your moderator. My name is Brett Little. As always, this course is approved for multiple continuing education units, as well as LEED AP professional homes, certified green home professional in the energy and water pillars, AIA health, welfare, and safety, which may make it applicable to your design-based or contractor license. Just wanted to say we would encourage you to become a member if you can, support our sessions, get free discounts on green building certifications, get discounts and free live trainings, discounts on air quality monitors, and also wanted to announce that we have a program manager job opening here. So you can check that job opening up. You can check out the membership opportunity. And we've got a couple of those mugs left there, corn-based, made right in the USA, sponsored by one of our board members, TrueTech Tools. You can check all that out, sign up, and learn more at the greenhomeinstitute.org. Get involved. Before we get started, a huge thanks to our top tier sponsor, Rheem. Real exciting. They are an Energy Star Award 2022 Partner of the Year, most energy efficient water heater on the market. 400% energy efficiency with their air source heat pump water heater up to that. The way these systems work, and we're going to talk about this a little bit later, the way they work is they pull in air at the top, and it's warm air, there's heat in the air and all the time, and it passes through a filter, gets into a refrigerant, hits the compressor, there's condensate, heat is transferred into the tank, and the condensate goes away, and you and your clients get nice hot water. All sorts of benefits, again, up to 400% efficiency, way better than standard electric or gas. There are different operation modes as needed, better warranties, leak detection, and works with home automation systems. So you can control it, your clients can control it all on their phone and get a lot of information, operating schedules, all of that as well. These things can be ducted if needed, if they're in tight enclosed spaces, or they can be strung together for multifamily housing development. We've seen that. And one cool thing is these things can basically act like batteries, and they're being paired with time of use, peak load shaving, DER, in whatever way you want to say it, programs all across the country. It's just a matter of time before this program shows up in your backyard. And this is what I do too. I heat my water off peak when costs are low, carbon is low, and then the system just doesn't really run unless I really need it during peak time, and then it fires back up again when peak goes down, carbon goes down. That's the future of how we're going to be heating water heaters. And the other great thing is they're going to be first to market with a 120 volt, 15 amp circuit. So we really say this is heat pump water heaters for all, because most people just can't access and pay for all the electrical upgrades. This is going to get heat pump water heaters to the mass market. So stay tuned, check all that out, and check them out over at Rheem. And then our second tier sponsor, Niagara Conservation, bringing water all the way down to 0.8 gallons per flush. We're talking about vacuum assisted technology that works. We have multifamily housing developers in the affordable housing renovation sector that swear by this. So you know if it works there, it'll work anywhere. I've been using this system for over a decade. But hey, if you're a little nervous about 0.8 gallons per flush, they have a whole lineup coming your way that's all water certified, that can save water and still get you to the need that you want. So check out Niagara Conservation to learn more. All right, so before we get started with our session, Practically Perfect Plumbing Part 2, just a reminder for the LEED component of this is that we're looking at LEED BD&C V4 and V4.1 residential efficient hot water distribution systems, up to 5 points available for that. And so here's a snapshot of the checklist. What we're looking at is circulating pumps and some different ways that they're being set up and designed as one way to score some different points. And then along with that, we're looking at having certain pipe lengths set up as well, which we're going to talk a lot more about throughout these sessions. And then also that includes pipe volume, very important. And so there's some requirements there for lead to have proper pipe volume, proper pipe lengths, if you're taking option 1. Now, performance testing is really what it's all about. That will tell you if you got your time to tap, and that's what we talked a lot about in session 1. And so this ultimately, if you can do that test with your rater and you can verify that the performance is there, and by doing the things that are being mentioned today, you're going to get that performance you're looking for to get those points. And then ultimately, you can score some additional points along with that simply by just putting pipe wrap up to R4 on the hot water lines. So that can be done in tandem with these, ideally, or it can be done as a standalone as well. So those are all ways to score and lead, and we're going to get into much more detail throughout this session. And so with that, I am going to stop talking and hand it off to our speaker. Really what's going on is, Gary is just in hot water again. And so it's really good to have him back. And, Gary, please take it away.
Thanks, Brett. Welcome, everybody. We've got a lot to share this morning, so let's get started with the presentation. We have something really fun to share with you in just a minute. Let's get started. We talked last year, it was recorded, all about what we were working on with Practically Perfect Plumbing. We went through a bunch of details on pressure and flow and right-sizing the plumbing. We've got some updates for you. Learning objectives, you can read all about them. They're on the website. Just a reminder, water consumption. This is from California, but much of this is applicable across the country. We've reduced the water used by lots and lots of things by somewhere between 50 and 96%. That's a huge reduction in water use, but nothing has changed yet for sizing the plumbing. All those rules are written down in around 1940. The pressure laws through pipe fitting numbers were published in 1941 and have been replicated by everybody since. What's useful to note is that the research on pressure loss through pipe fittings was actually done in 1892 and published by the guy's son in 1941 for steel pipe and threaded and flanged fittings, and I'm pretty sure we're not installing that in modern buildings for our domestic water. What are we aiming for? People want the water to feel right. They want their toilets to flush first time every time. They want clean clothes, dishes, and bodies. They want the service of hot water as efficiently as possible. And quite frankly, I don't think we should talk about efficiency until the desired service has been provided. I've been working on this question for quite some time. And one of the things that I've been sharing a lot for the last year or so is about the question of where did all the pressure go? Why does your shower feel wimpy, and what can you do about it? Well, in existing buildings, it's a little harder to do much about it because they're existing. It's hard to change the plumbing. It's expensive. But there's things that happen in new construction that are inadvertently happening because we're not paying attention to the pressure loss through all the components properly. And what I want to share with you today is a video that we took a couple of weeks ago in Ann Arbor with the Plumbing Union's training trailer that they have to teach plumbers around the country about these questions of pressure loss and time to tap. So Brett, if you could, can we share the video? I'll stop sharing. It's all yours.
Hi, my name is Gary Klein from Sacramento, California. I teach plumbing design for a living. We're here on the UA's training trailer ST1 with the water module we designed in 2016 to teach about pressure drop in modern pipe and fittings, time to tap waiting for hot water to arrive, heat pump water heaters, which are coming along as part of the electrification efforts and decarbonization efforts in the US. And we're going to show you how to pick an aerator that'll make you happy. My goal in the next 30 minutes is to teach you 5 things you didn't know about water. Are you ready? This water heater is installed incorrectly. Tell me what's wrong. Let's look around it. There's a drain plug there. That looks good. Electrical probably looks okay. We've got the wiring hooked up. We have a pan to collect any discharge from the T&P valve. That looks pretty good. We have a drain for the heat pump. This is a heat pump water heater that's got condensate. There's a condensate drain. So what's wrong? I know it's installed incorrectly. So heat pump water heaters use air to make heat. They capture energy out of the air and they use it to heat the water. Sort of like a refrigerator in reverse. And the heat pump's about the same size as the one under the compressor under your refrigerator. All good? This is the inlet. Where's the outlet? If we reach around back, for here, you can feel the air coming out. So what's the problem? We forgot to read the manufacturer's instructions. The manufacturer's instructions say it's supposed to be 7 inches of clearance to the wall, and we only have 3.5 to 4. So it's installed incorrectly. Okay? It still works, but it's not what the manufacturer said they needed. Now the other part of the thing, so that's one. That's one thing we didn't know, right? Water heaters have filters. This is an inlet filter. It's a screen. It's to collect dust bunnies and pet hairs. Why? There's a coil inside here that gets gunked up if dust bunnies and hair get on it. And now you have to come clean it. In the meantime, the efficiency of your water heater that you just bought went down. How much? A lot. Okay? And so one of the things we have to be sure to teach people about is the airflow for heat pump water heaters, in and out, and that we have a filter that we have to pay attention to. This heat pump has the opportunity to run on 4 different modes. We have it set on heat pump only mode. We could be a hybrid mode, which is a combination of heat pump and electric resistance. We could be resistance only, and we could set it for vacation when we go away. Okay? There's 3 or 4 manufacturers of what's called unitary heat pump water heaters here in the US. They all have similar product. In the next 2 or 3 years, we're going to see 120 volt heat pump water heaters that you can retrofit into houses that don't have big 240 amp service for water heating. All that stuff is coming. It's part of the electrification push in the United States to decarbonize how we make heat. So that's part 1. Now let me tell you about what we have here. We're on a trailer, and we had to figure out how to bring a whole water system here on the trailer. Down here in that silver tank, that's our reservoir. Stores 150 gallons of water or so. Here's our pressure pump and pressure tank to create system pressure. They're right in the middle. We currently have pressure set at 80 psi, which is about the maximum allowed by most plumbing codes for going into buildings. This is our hot water source, and we have the ability to choose in and out for hot water or just cold water. The cold water goes, all the water we measure goes through this flow meter, so we can tell how fast the water is moving. And here's our plumbing system over here on top of the tank. To create flows, we have a sink, which if we turn it on, gives us a flow of water. This one's about 1.6 gallons a minute. Or if we really need lots of flow, we have bypass valves over here where you can move the water very quickly, up to 10 or 15 gallons a minute. So this is our system. Now we're going to do some experiments. We're going to teach some things about how water moves. So let's try pressure drop through modern pipe and fittings. If you look here on the rack, there are 5 different combinations of pipe without fittings, pipe with fittings. That's Pecs, Cpvc, copper, all in 1/2 inch. And then we have 3/8 Pecs with and without fittings and 3/8 copper with and without fittings. There are 50 feet of pipe with and without fittings for each combination. When you have elbows, in this case, there are 14 elbows in the system. So let's do an experiment. Let's pick one of these pipes. How about we pick 3/8 Pecs, no elbows, and we'll measure the pressure loss at about 1.5 gallons a minute. We'll set it up for that, okay? So we open the valve to decide which one we want to run. We're going to watch that flow meter, and we're going to watch these 2 pressure gauges. This is pressure in, that's temperature in. This is pressure out, that's temperature out. Pressure is measured here and here. Temperature is measured here and here. So we're ready to run the test. I'm going to turn on the tap, and we can in fact watch all of our pressure gauges right here on my screen on the iPhone. It's a very clever system from Fluke. It does Bluetooth to the phone or your iPad, and you can literally diagnose what's going on in your equipment pretty quickly. So I'm turning on the flow, and the flow meter is up there over the water heater. And why don't we pick about 1 gallon a minute? Instead of 1.5, we'll pick 1 gallon a minute. Nah, let's go up. I like 1.5. And it looks like we're there. About 1.5. Let's got hung up on it being too perfect. All right? So, what do we have for pressure loss? We have on the 2 gauges, we have P1 is at 74, P2 is at 61. We're losing about 13 psi at that flow rate. Okay? Now what I'm going to do is go switch to 3/8 Pecs with 14 elbows. All I've done is switch from one pipe to the other. Let me check my flow rate, which by the way went down from 1.5 to 1.36 because there's more resistance. Now I'm going to try and bring it back to 1.5 gallons a minute, and I can't do it with this aerator. There's that much resistance to pressure. So what's the pressure drop we're going on here? 79 minus 46, so that's 33 psi of pressure drop. That's because of the fittings. Insert fittings make a big difference. Okay? So here's an example of what we actually have on the trailer. These are the pipes that we're testing on the trailer and the fittings that go with them. 1/2-inch copper, 1/2-inch CPVC, 1/2-inch Pecs, 3/8 copper, 3/8 Pecs. Copper 1/2-inch fittings, CPVC 1/2-inch fittings, Pecs 1/2-inch fittings. 3/8 copper, 3/8 Pecs. And if you look carefully on the insides, you can see how big the inside diameters are, both of the pipe and of the fittings. And what you notice is that the inside fittings, the fittings for Pecs that are insert fittings, affect the waterway. They're inside the pipe. The copper and CPVC are outside the pipe. So now let's switch to another pipe. Let's go to 3/8 copper, no elbows. What's our flow rate? Without changing anything, went up to 1.6 gallons a minute. I'll bring it back to 1.5. And we're almost there. Okay. And now we can look at the pressure loss. Oops, went down a little too low. The pressure loss is 75 minus 73. It's only 3 psi, 4 psi of pressure loss. Much less loss for the same flow rate in a different type of pipe. Well, why am I so focused on flow rate? Customers want their showers to feel right. They want 1.5 gallons a minute at their faucets. They want 2 gallons a minute at their showers. Whatever it is they want, we want them to get. And we have to design systems that give that to them. So we have to understand and account for the pressure loss in the pipe and the fittings. Now let's switch it to copper 3/8 with elbows. And we're at 1.5 gallons a minute, a little bit less. And you know what? We still only have 5 psi of pressure loss. So all those 14 elbows in copper only added 1 or 2 psi to the pressure loss at the same flow rate. Not much loss for those fittings, right? That's the point. All right, let's do one more experiment because it's fun. Let's pick CPVC 1/2-inch. We'll go to no elbows. Elbows, we're going to run 1.5 gallons a minute. Didn't change much when we went from 3/8 copper to 1/2-inch CPVC. It turns out the inside diameters are similar when all said and done. And we're at about 1.5 gallons a minute. And our pressure loss is 78 minus 75, 3 psi. Okay, so the system without any elbows for CPVC is similar to copper with 14 elbows. One more experiment. Whoops, I've got them both open. I don't want them both open. Now we have CPVC with 14 elbows, and the pressure loss is still only about 3 or 4 psi. Outer fittings don't affect pressure loss as much as insert fittings do. That's the big deal. So we have to pay attention to it. All right. Now before we leave pressure drop and pipe and fittings, I want to show you some of the experiments we've done. Why is it so important? First question is, where did all the pressure go? Well, the plumbing code says we're not supposed to have more than 80 psi going into our buildings. Most of us don't have 80 psi to begin with. We have 60 to 70. Sometimes we're as low as 40. So this discussion is about where did all the pressure go and why your shower feels wimpy. You start out with 80. You lose 9 in pressure loss when you go to the second floor. You have no choice. It's elevation. There's losses in pressure through the anti-scald shower valves that are required by code now. And then there's losses in the plumbing, and I'm going to say they're about 20 psi. In some cases, 20 is a high number. In some cases, it's a low number. I can explain where all of these come from. When you're done, you're losing somewhere around 40 psi when your shower is flowing. Well, that means you're only got 20 to 40 psi coming out of the shower valve headed to the shower head. Here's the problem. Shower head flow rates were determined at 80 psi. And if you only have 40 psi, you're going to get 1.4 gallons a minute. And if you only have 20 psi, you're going to get 1 gallon a minute. And if you didn't think you liked 2 gallons a minute much, you're going to hate these other two. There's similar things that happen with faucets, but they start at 60 psi. So what we're going to do is jump. Oh, I got to go this one. Here's the rules. This is the bizarre part of all this. The pipe sizing rules were written down in the 1940s by a fellow named Roy Hunter with the National Bureau of Standards. That method of sizing water piping in buildings is still in use today with numbers from the 1940s. Nothing flushes or flows at those rates anymore. So why are we using those rules? Okay? There's something else we should know is that the pressure loss in the pipe fittings was published in 1941 by the son of the guy who did the research in 1892 for steel pipe and threaded and flanged fittings. And we don't use that for our plumbing systems either anymore, for domestic water systems. So why are we using those old numbers? Because that's all we have. So I decided to get new numbers. That's what I've been working on for the last 10 years. We know about time to tap and volume to hot. We'll get to that. There's a new method of sizing water piping called the water demand calculator. You can see the link here. It'll take you to the home page of the website that has this on it. You can use it in any jurisdiction in the United States. It's a standard that was developed by IATMO. And it allows you to right size the plumbing for single family, multifamily, and single apartments within multifamily occupancies. We're working to extend it to other occupancies, but we haven't got there yet. We've set up a lab. You can see this one, that's version 1. It's very similar to what's here on the trailer. Version 2 is here on the trailer. Version 3 is up in Arcata, California. And what we've done is we have a testing cart and we have the test segment cart. See the rectangular spiral? There's 10 elbows there. And instead of 50 feet of pipe, which is what we have here on the trailer, there's 16 feet of pipe with and without elbows. You can see some of the things we've tested. I want you to pay particular attention to elbows, sweeps, and swoops. And I want you to pay attention to the tight radius, the tight corners, the hard 90s, and this long radius bend support. We've looked at couplings and tees, and we have data on the pressure loss in modern pipe and fittings. Here's one of the most important things to pay attention to. I've circled 2.9 gallons per minute here because it's 4 feet per second. That's the flow rate I have to set this equipment at in order to get the pressure loss that we're measuring here. And so at 4 feet per second, 2.9 gallons per minute is higher than virtually everything flows in a dwelling today. Right? Legal shower heads in the US are 2.5 gallons per minute, but that means there's only some on the hot and some on the cold. It's not all hot or all cold, so it's less, right? Bathtubs are filling at about 2.93 gallons a minute. Big master tubs with a 3/4 valve on them, they might flow 7 to 10 gallons a minute. They're bigger. Toilets are 3 to 5 gallons per minute when they're filling, even though they're 1.6 or 1.28 when flushing. Okay? What matters is the fill rate. So we're going to pick 3 gallons a minute, 2.9, and that tells us here the pressure loss is about 0.05 per fitting. There's 3 different fittings in here, and they're all around 0.05. Hold that thought. Now let's go to CPVC. To get 4 feet per second, I set my equipment at 2.3 gallons a minute. But I live in a house that wants 2.9 gallon per minute stuff. That's what I want, right? So now I have to look between 4 and 6 feet per second to get my actual velocity and pressure loss. It's right here around 5. It's 0.2 psi per fitting. So these fittings are about 4 times more pressure loss than the same fitting would be in copper at the same flow rate. It's 4 times bigger. It's a big deal. Now let's look at Pecs. Here's Pecs tees and couplings. Here's Pecs elbows. What we have here is that you can see groupings. This is one fitting type. This is another fitting type. This is a third fitting type. On the elbows, they range from 0 pressure loss to make a 90-degree bend to almost 6.5 psi per fitting loss at 10 feet per second. But here's the range. 2.2 gives me 4, 3.3 gives me 6. I want to be close to 3 gallons a minute, which means I'm sort of here around 5.5 feet per second. Well, if I read the number off at 5.5 feet per second, I'm about 1.8 psi per fitting. Not 0.05 and not 0.2, 1.8. If I'm here on the elbows at 5.5 feet per second, I'm about 2 psi per fitting. So for today's discussion, we'll use 2 psi. Why am I using the maximum? I do design work. I don't know what's going to be in the building until later. So if I'm designing a plumbing system, I want to make sure that if someone proposes an or equal, I have the chance of saying, okay, you can pick or equal because the pressure loss will be better when you choose that as opposed to the one I designed for. If I did my analysis with the pressure loss down here somewhere and someone picks one of these fittings, it's not or equal. The system is very different in the wrong way. All right, so we're going to pick 2 feet per second, 2 psi per fitting compared to 0.05 per fitting. I'm pretty sure if you do the math, that's 40 times bigger. We have to be careful of our choice of fittings, particularly when they're inserts, because they really do affect the waterway. All right, so look at that one at 0. That's a bend support. All right, we pointed it out earlier. That bend support keeps the radius of curvature big enough so that the water doesn't know it changed direction from a pressure point of view. It's a very cool thing to have. We can build that in copper. We can probably do it in CPVC, but we absolutely have bend supports for Pecs. So we tested this to try and see what the differences are. And what we found is that this is straight pipe. This is a curved pipe, sort of a lazy S in and out of our equipment. The green is a coil. Pecs comes in coils. We tested it in coils. And this is the 16 feet of pipe with bend supports in it. Notice how similar they are at 2, 4, 6, 8, and 10 feet per second. The difference, even at 10 feet per second, is 0.05 psi per fitting per foot, which is really in the noise of what we're measuring. Our equipment isn't that accurate. This is within the noise. So I'm going to say they're almost the same. And at 8 feet per second, which is the typical maximum for flow rate in the code, I'm somewhere around 0.3 psi per foot. If I'm at 6 feet per second, I'm about 0.18. If I'm between these two, I'm sort of here at about 0.15. So now I can calculate equivalent feet. I know my PSI per foot, I know my PSI per fitting, and now I can tell you how many extra feet it is for each type. We've done the same analysis for copper and Pecs at 3/8. I still want my 3 gallons a minute. In copper, I'd have to be a little over 6 to do it. So I'm up here, and the worst one is probably 0.3 or so PSI per fitting. Okay, it's smaller diameter. You'd expect it to have higher pressure loss. And in Pecs, to get 3 gallons a minute, I need 10 feet per second. The plumbing code doesn't want us to go past 8 feet per second in most cases. So we have to pick carefully the things we attach to 3/8 Pecs because of the additional pressure loss at the higher velocities. And if we've done the same analysis for the bend supports and curves, coils, and we've got straight somewhere, but these are bend supports. And you can see that they're all very similar, just like they were for 1/2 inch. Bend supports are a really big deal. What I want to cover now is the pressure drop through tub shower and shower valves. Look at the picture. We've got valves from different manufacturers, all US brands, in price points between about $85 and $150. Stuff that goes in most of our homes, most of our apartment buildings. And what I did is we set up an experiment using our pressure lab to look at the pressure loss when the water flowing through the valve, not through the shower head or the tub spout, but through the valve, was 0.5 GPM, 1 GPM, 1.5, etc., as far as I could go until I ran out of available pressure in my lab. And so and that's at about 50 PSI, by the way. And so what we find is this. If you have a shower head at 2 gallons a minute, the shower valve with the least pressure loss is around 5 PSI, and the one with the most pressure loss is about 17 PSI. And so when you're designing, if this is the range, you'd pick the 17 to 20 PSI per shower valve loss. And when you come back with an or equal, it's going to be less pressure loss in your system. It's a really good idea for doing it that way because you don't know what's going to actually get built when you're doing design. If you know, then you can build for it. My recommendation is to put in a bit of a safety margin. It's always good to have less pressure loss than more. So that's what we try to teach. We've done the same thing with tub spout fillers. And what you find in most buildings is because of the drop through the valve at 3 gallons a minute, it's 30 PSI through the valve. You're up on the second floor. You only started with 50 PSI. You only have 10 left. And the problem is you need more left in order for the valves to work right. And so we tend to see flow rates are claimed to be 4.5 gallons a minute. We rarely see that for most tub spouts. But this tells us what to expect. Now I want to show you something about faucets and shower heads. Remember we talked earlier about the 80 PSI coming in and losses for elevation, losses through the valves. I picked 11 in the example, and then there's a bunch of loss in the piping, right? So what we have is this. If you buy a shower head, it's rated at 80 PSI by its product standard. If you only have 40 PSI, instead of 2 gallons a minute, you're going to get 1.4 gallons per minute. And if you only have 20 PSI, which some folks do, you're only going to get 1 gallon per minute out of the fixed orifice shower head. What if you could have an orifice that adjusted for pressure, which it kept the flow rate more similar to what you bought at 80 throughout a wide range of pressures that are available? So 85% at 20, 98% at 40, and all the way out to 80 PSI and more, you're going to get most of what you thought you bought. That's what customers want. That's what I want people to buy. And it's the flow regulator for the showers looks a lot like this one for faucets. That O-ring is what compresses when pressure is high and relaxes when pressure is low and gives you more constant flow over a wide range of operating pressures. That's what we're teaching. Now, let's switch it to faucet aerators. Faucet aerators are really cool. They're rated at 60 psi. How come they're not rated at 80? I don't know. It's the product standard. All right? But it's at 60, and the same problem occurs. That gray line is the normal pressure flow curve. If you start with 2 gallons a minute at the faucet at 80, and you only have 30 psi, you're going to get 1.4. And if you only have 15 psi, you're going to get 1 gallon a minute. If you buy a faucet aerator with one of those single cores in it, right, you'll get 78% at 15 psi and 94 at 30. But if you could get one with a dual core pressure compensating aerator, which you see here, you're going to be on the gold line. And the gold line means you get 95% from 15 psi on up. That's what I want in my house. Why? I don't know what the pressure is going to be at any given time. No one knows. But I want my faucets to operate what I thought I bought them at. 1.5, 2, 2.5, whatever it is, faucets and showers, I want them to operate close to what I bought when they were rated at their pressure for the test. That's what we're looking for. All right, now let's go back over here and do another experiment. What I'm going to do is to set the flow rate in cold, and then I'm going to switch the valves when we say go. And then what we're going to do is watch T1. We're going to lap it when it starts to rise. And then we're going to watch T2, which is over here, and we're going to lap it again when it starts to rise. We'll lap it one more time when it comes to 105, and we'll stop it when it hits 120. That's the experiment we're going to run. Okay? So first I have to set flow rate. And we're going to set it at about 1 gallon a minute. The reason we pick 1 gallon a minute for this simple experiment is because we can do all the math fast in our head. Doesn't matter what the flow rates are, it's all proportional. So we are at just about 1 gallon a minute. You can see it up on the flow meter. I'd say we're pretty close. And we'll get ready to do our test. So here's what's going on. Between T1 and T2 is 0.6 gallons of water in the pipe. If I'm moving water at 1 gallon a minute, we would expect to have hot water arrive in 36 seconds, 0.6 times 60. It's going to take longer. The question is how much? Why does it take longer? At a minimum, we have to heat up the pipe on the way. And while the water's moving, it's not all heating in the perfect way. It's mixing and doing other things going on in the water, so it takes extra water to come out before hot water gets there. And now we're going to run the experiment. We're going to switch the valves and start the clock. Are you ready? Go. We're watching T1. It's at 76, and we're going to lap it when it starts to climb. And we'll see it start to climb now. And we lapped it. Now it's 89 degrees. You can see it climbing over here. T2 at this end is still cold, 76, 77 degrees. When it starts to rise, we'll lap it, and that will happen in about 30 to 36 seconds from the start. We're currently at 36 total. We have to add 10 seconds. So at 40 something, it should start to rise. Now, there we go. That's how long it takes to clear out the cold water that's in the pipe. And now it's going to start to rise. Notice that T1 is already at 130. T2 is climbing. When it hits 105, we'll lap it again. Why 105? That's the temperature I'm willing to get in a shower at. If it's cold, I don't want to take one these days. 95, 97, 99, 100. It's climbing quickly now. 103, 104, 105. And now we're going to wait for it to hit 120. And what's interesting about this is, I don't know about you, I'm standing in my shower, I'm willing to get in at 105, But as the shower warms up, I have to adjust the mix on the shower valve. It's all because everything is warming up. And we'll stop the experiment now. All right, so let's talk about the lap times. Took 10 seconds for hot water to reach T1. It took another 36, 37 seconds until the temperature at T2 started to rise. It took 116 minus 10 is 1 minute 6 seconds. Call it a minute, it's close enough for this estimate. It took 60 divided by 36, not quite 2 to 1, for the hot water to actually reach 105 at T2. And then it took additional time till it reached 120, and that's what happens when you're in your shower, when you have to adjust the handle a bit more cold because everything's warmed up. What I want to show you now are how different aerators work. The first thing I want to show you is to look at the little air gap here on this flow regulator for faucets. We call them aerators. The air gap means that it's bringing in air and it makes champagne bubbles. This aerator doesn't have an air gap, so it's going to give you a clear column of water. And we'll demonstrate that in a minute. And the last thing I want to show you on these two, which are the same flow rates, maxed out at 1.8 at 80 psi. If you look very carefully, there's a little toggle here on the front of the aerator, and you can adjust where the flow rate actually hits the sink. If it's not centered quite right, you can recenter it. It's very cool. So what I'm going to do is to put in the first aerator. Got a problem. First, I'll put in the aerator with the holes. You know, I don't know why we call them aerators. Aerator means to add water to the air to the water, right? But we all call them aerators, no matter what they do. And there's a lot of choices, way more than you would have guessed. Hey, Dan. So, here is champagne bubbles. It's foamy. You can see it, right? And what we're able to do, I told you about that toggle, I can change where the water hits the sink just by adjusting it. Now let's take that out and put in laminar flow. Same flow rate, different stream flow. Turns out there's 5 different stream flows for faucet aerators, right? There's lots of different tips. There's lots of things you can get as special features, but here's the basics. Laminar flow. It's a clear column of water. Some people like clear columns of water. Other people like things that look like a shower head. Other people want foamy bubbles. You can pick the flow rate and pick the stream flow. Now I want to show you one of my favorite low flow aerators. This is for public hand washing sinks mostly, but hey, you could use it in your house if you like it. Particularly in the powder room where people are just rinsing their hands anyway for the most part. And this one, called Mikado, looks like it's someone weaving a basket with water. It's really very nice. And it cleans your hands, which is its purpose. Thanks for watching today. I hope you learned a bunch.
Cool. All right, so let's continue along. I hope the video was helpful. I think it's fun to watch the water working and moving, and so I figured you all might want to see how I go about getting all the information I share with you. Let's talk about reducing time to tap. Then ultimately, we've talked about the pressure drop. I'm not going to go over that again today. And we'll talk about right-sizing plumbing before we finish up today. All right, so we're given a floor plan. Some of us on the call are architects, others are builders, others are energy raters. The architect, and if the client's involved, the client decide on where to put the wet rooms. The bathrooms go wherever you choose. Some people want to have a big bathtub with a view out the back window. My house in California comes with one of those big tubs with a view out the back window. I'm fortunate, I actually have a view, but a lot of people have exactly the same house with exactly the same bathroom, and their view is of the neighbor's window across the two lots. And sometimes the view is good and sometimes it's not so good. But people do that all the time because that's the way the production construction happens. And so we are in the architect and the client decide where the wet rooms go. Once that's decided, the builder and the plumber have no choice but to put that in and connect A to B so the water doesn't leak. We did a pre-search project for the state of California. The final report has been published, where we examine the architectural compactness and what would happen if you were able to reduce it from what was typical to something that was more compact, putting the wet rooms closer together. The research on that project analyzed floor plans using this hot water system rectangle idea, where you bound the water heater and all of the fixtures with a rectangle and compare that size to the area of the house. And in a one-story building, the logical worst case is 100% of the floor area is related to the hot water system. We've seen as much as 155%, and we've seen as little as 1%. There's a huge variation. But mostly what we see in new construction is somewhere in the 70 to 80% range throughout the country for one-story buildings. Now let's look at some buildings that were provided to us to look at by members of this group. We took a floor plan and we did a one-zone hot water system. What did we do? Water heater is up here in the mechanical room. We have a sink here in the lounge, right? Wet bar. We have a bathroom up on the second floor. All of the plumbing is on this wall. I'll come back to some things I see in the plumbing in a minute. And then over here, there's an island sink in the kitchen. And the master bath is all the way over here in the diagonally opposite corner. Oh, and we decided to put a shower and a sink out in the garage. So we have a rectangle that bounds all of that. And the area of that rectangle is 59%. Well, in a two-story dwelling, the logical worst case is 50%, one floor over another. So this is a little bit more stretched, if you will, than the logical worst case for a two-story dwelling. A few things I want to point out before we go on. I like the drain here in the shower along the wall. I have a suggestion: move that drain to here and have a walk-in shower. And then what we do is we slope the floor of the whole bathroom toward that drain. It's called insurance, right? If the toilet overflows, where's the water going to go? To the floor below. And it becomes a very expensive proposition. If we could figure out how to create wet rooms that drain to a floor drain that gets used on a regular basis, they stay wet, don't go dry, don't get smells, and we have insurance that our house will stay fine in the event of an accident. I like to see floor drains in utility rooms too for the same purpose. Water heaters, if they decide to fail, or when they decide to have a leak, we don't have a choice over some of that stuff. I want to make sure that any water can get out and go down and out of the building without a problem. A pan is not adequate for the purpose. It's a catastrophic failure that matters, not a drip. This is a problematic fixture here in the kitchen. It's an island sink over a slab on grade construction. That means we have to run plumbing under the slab to get to it. In California, we have rules related to underground plumbing that say that you have to run the plumbing to the sink in a conduit so that you can pull the pipe out and repair it if you ever need to over the course of the building's life. And if you have hot water piping, you have to make it so that you can insulate the pipe too. We wanted to be able to do that. So the question becomes, which wall are we going to go down to get the pipe underground to that sink. In many cases, it's actually the outside wall is chosen because we know where that foundation wall is going to be when we build a house. We're a little less clear about the walls in the middle. And so if I were trying to do this, I'd be coming down one of these walls here and headed over to the sink rather than all the way out to the outside wall to come back again. It's a little bit more distance under the slab. On the other hand, the total run of pipe is shorter, and that's always a good idea if we can do it. All right, let's move on to the next one. What if we thought of the plumbing as a 2-zone hot water system rather than a 1-zone hot water system? And instead of one big rectangle, we look at it as 2 smaller rectangles, right? The water heater is somewhere right up here right? It's up here. And so as long as the water heater is roughly at this point, that's the right bounding conditions for both of those rectangles. And if we design the plumbing as some plumbing goes this way and some plumbing goes this way, we'll have 2 smaller diameter systems because we've separated them from 1 to 2. And the ratio goes down to less than 50%. Now let's look at one of the projects provided by Jake Viersen, who's on the call with us today. Jake, are you able to join us?
I am here.
Cool. So this is a project that's I guess is still it's being ready to get built. Is that correct?
That's correct. I'm still in design, or rather in pricing.
Got it. So the design was done. You're the builder. You were given this floor plan, and now you're going to hire a plumber to put everything together.
Correct.
And we've talked about this earlier today. The hot water system ratio is about 50%. It's one floor above the other floor. Why did we get 50%? The mechanical room is up here. I think that's the second floor, but I don't know where the water heater is going to be in that space yet, right? So it could be on the outside wall. It could be on the inside wall. It's got to avoid those closets, those doors. So we got to pick one of the sides to do. I don't know where it is. I've assumed for the moment it's an outside wall. Okay.
All right.
And so with the water heater here, I have a toilet there, so I didn't have to go quite that far. The sink is there, the sink is there, right? There's the lavvy. There's the shower, the tub shower valve. I like that. Oh, I had to go all the way to the outside wall because on the first floor, there's a sink right on the outside wall. So I have to go from left to right across the whole space. The laundry sink is here. The kitchen sink is here. I now have to go to all the outside walls to bound the rectangle. Does that make sense, Jake?
I follow you. Yep.
Okay. So it's about a 50% system ratio. Whatever the area is, it's one up, one down. It's pretty close to the logical worst case. One thing I want to point out here that I like, and one thing that I'm not sure about, and I hope you get it right. I like that the shower valve is likely to be here on this wall, not on an outside wall. Why? You're going to spend nice money making a shower surround. It's either going to be tile or fancy plastic or something like that because the homeowners want to do that. I'm going to suggest to you that over the life of the building, that shower valve may need to be worked on. And if that's true, I'd like to go at it through the sheetrock. Sheetrock is much less expensive to repair than tile. Okay? I really like that idea. And over here on this shower only in the master suite, I would like to see the shower valve on this wall on the inside rather than on the outside wall of the house for the same reasons. I have no way of getting in to fix that valve. I have to go in through the front. And that just becomes an expensive proposition over time. Okay?
Great points.
So those are things I think about a lot. Sinks. This house does not have a basement. Is that correct?
Correct.
Okay, so this is a classic case of there's a window over the sink. I think that's a law. Any architects on the call? I think that's part of your code of conduct as an architect. You have to put a window over the kitchen sink. Just don't take it wrong. So the problem is that the people who make dual pane windows do not want you to put, or triple pane windows, they don't want us to put our plumbing through their glass. So you cannot come down from above straight to the sink. You have to come around it. And so if the water heater is over here in the mechanical room, the shortest distance to that sink is probably along here, down this wall and over to the sink. Somebody's going to put something in the way of that being possible. There's going to be some framing members or some structural supports. The steel guys get involved. The structural engineer says, I got to make this a super panel. For whatever reason, you can't follow the shortest path. You don't always get the shortest path. But we have to figure out that. And so the distance to the kitchen sink is actually often longer than people expect because you can't easily get there. Okay? Now, let's try one more thing. Let's see if we could make a two-zone system. And in this two-zone system case, we split the building into two parts because there really isn't any water in this part of the building at all. Fair enough?
Yeah.
And since I don't know where I have to go around the kitchen sink, whether I have to go to the right side or the left side, I pick the rectangle as being relatively large, and I pick the far end of the room above where the mechanical room is. Okay, that's a good approximation of that rectangle. But everything else is actually pretty tight on that side of the building. And if I could make the mechanical room, if I could guarantee that the water heater would be over here in this corner, I could make this a much smaller rectangle. I could come up to here. I just have to get to the valves. Does that make sense?
Mm-hmm.
And so the point is that we have to follow the plumbing. We don't have to follow the room, right? But we have to follow the plumbing to make sure that we're covering the spaces involved. That's the idea of this rectangle. And now we're down around 38%, which is better than 50%, right? We're on the right side of logical worst case. We're better. This is good. And so we should be able to design that, and I hope some of these ideas will be helpful when you actually get to construction. All right, let's move on.
Well, real quick,
ahead.
since we have Jake here, Gary, and since one of the first questions, undoubtedly that came out was about cost. Jake,
Right.
just looking at some of these recommendations, obviously, and I know just kind of putting you on the spot, but I mean, do you think some of these things are practical cost-wise or could be helpful even?
I think what Gary just proposed on this house shouldn't affect costs at all. As far as I'm concerned, it's just a little bit of planning and doing it a little bit different. We'll see. I'll definitely be having a conversation with our plumber about this. I'll probably take the video to him.
Yeah. Okay. Well, thanks. I just wanted to get a quick thought from you on that one. And
so, Jake, you have permission to call me when you talk to the plumber. Okay.
Excellent. Thank you.
Give you a little bit of extra consulting for helping out here today. I want to see buildings get built right, and I love to hear what people think why it can't be done. Anyway, let's move on. All right. So I want to right-size the plumbing now. I said we would talk about that. We have available to us a new method of sizing water piping that's based on modern information, unlike the stuff that's embodied in all of our codes. The water demand calculator is a method for estimating the demand loads for the building water supply and principal branches for single and multifamily dwellings. What does that mean? It means from the water entrance to your building, including the size of the meter, all the way through to what I call the twigs. So there's trunks, branches, and twigs. The trunks come from the water main. There's a branch that goes to the water heater to make the hot water system. There's a branch that goes off to feed all the rest of the cold water in the building. And then the twigs are what you connect to. Your faucets and your showers and your toilets all get connected by a twig to either hot or cold or both. Okay? The water demand calculator does not address the size of the twigs. It addresses the size of the branches and mains. All good. This is showing you the results of a calculation for a 24-unit apartment building. You can see that The number of fixtures is 74. The peak estimated 99th percentile peak is 17.5 gallons per minute. During the peak period, 1.2 fixtures are operating at the same time. That's not very many. And the probability there's no flow is only 30%. So we're expecting that there's a relatively high likelihood that there will be simultaneous events. The benefits of using the water demand calculator: you get water and embedded energy savings. You get energy savings due to decreased heat loss in the hot water system, particularly in multifamilies with recirc. You improve the water quality because there's shorter dwell times in the plumbing system. You get construction cost savings because smaller pipe saves money in lots of ways. I'll show you that in a minute. Standard practice overestimates peak flow rates. You see those little dots down here at the bottom? Those are 20 different apartment buildings where we've measured the peak flow rate, the 99th percentile peak flow rate. And now you can see we're looking just at this part of the curve, and you still see that you can see the letters and the dots now. Great, and they're not even close to the red line. The red line is the plumbing code prediction for that building. And here's what we've measured. And now we're looking at it in some detail. The black dots are the measured peak flow rates. The blue crosses are the water demand calculator estimates, and the red crosses are the Appendix A from the Uniform Plumbing Code design estimates. This is the plumbing code. The IRC, the IPC are similar to these numbers, the red lines here. But the water demand calculator is what you see. Water demand calculator can be used in all jurisdictions in the United States. You access it in different ways depending on your code jurisdiction. You have to ask at the moment, you pretty much always have to ask for alternate methods and means, but if you're using Appendix A or E in the IPC, you have to ask for that anyway. This is just another way of right sizing. It's very, very helpful. We've used it in upstate New York. I've talked about it before. It's been in design now in several parts of the country. I'm aware of over 5,000 single-family dwellings having been built using this method, probably closer to 6,000. So here's the impact. This is looking at an example of Seattle, New York, Washington, and Utica, New York. Different number of apartment units. You can see that the codes pick the various diameters, Uniform Plumbing Code, International Plumbing Code, and you sort of work through the math for each building, and you end up with a rather dramatic reduction in pipe diameter because the estimate of peak flow is so much different. Notice that we've never measured more than 4 gallons per minute hot or 5 gallons per minute cold. So even 10 gallons per minute, as the water demand calculator estimate would be, is still a good safety margin. But can you imagine going to the plumber and the building officials and saying, well, instead of a 3-inch main for my 35-unit apartment building, I want to put a 1-inch main in? Some version of "you've got to be kidding" will come out. But it works. It's true. We've got data to support it. The right sizing of the plumbing saved first costs. This is showing you from 2020. It's almost 2 years old now when I did this estimate for an apartment building in Seattle. We took the plan from the architect and the plumbing engineer. We redid it with right sizing according to the water demand calculator, and we got rid of all the fat pipe. And that saved us about $5,000 in first costs. When you take all of those costs and you add up the right sizing of the rest of the plumbing, remember you get the hot and the cold, you get all the fittings, you get the pipe insulation, you get the hangers, you get all of the valves and other pieces of equipment that are in the mechanical room. You get to right size the water heater, which is a big deal. You get to right size the meter, which is also a big deal. And your first cost savings are somewhere between $600 and $1,200 per apartment in first cost reductions, based on 2020 dollars. I'm sure it's worth more now. And then you get annual operational savings. At the moment in this chart, only those shown are for the water costs. We're not including any energy savings, and you will get energy savings. Why? Smaller pipe takes less volume to clear out, and if you have to clear 1.5 to 2 times the volume each time you want hot water to arrive, you'll save some energy there, and you'll save energy when you're running a smaller diameter recirc loop. So, given human nature, it is our job to provide the infrastructure that supports efficient behaviors. And now it's time for discussion. Brett, back to you.
Hey, thanks, Gary. Yeah, we've got some time for questions here. So before we get into those questions, just wanted to remind everybody real quick that here we go. For those of you who want to rewatch this session or didn't get to catch it all, you can head over to our YouTube channel in the next couple days. You can click subscribe there. You'll get an instant update when the session is available. And you can catch part 1, Practically Perfect Plumbing part 1, if you want to catch up on that session before watching all of this one again. For those of you watching this in the future on demand, not right now, go ahead and take the quiz with an 80% passing rate. You can check that quiz out on our Thinkific channel or USGBC channel and get your certificate that way. For those of you watching live, as long as you have been here at least for the full hour of the CEU and you've logged in appropriately to Zoom on a phone app or a computer, you can check your spam in the next couple of days at certs@gutenbergcerts.com. You'll see your certificate come your way. And before we get into some of those questions, again, huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, and all of our top tier sponsors, Mitsubishi, Rheem, April Air, and all of our sponsors who support our work to do what we do. So let me take a look here. Please clarify if the bounding rectangle, so this is a question, Gary, please clarify if the bounding rectangle should include all fixtures or only the fixtures with heated water. And maybe, following up on that too, on that calculator you were talking about, I had kind of a question to add. Was that only calculating heated water, or did it, for water savings especially, or did it include, toilets and outdoor landscape as well?
Okay, so 2 questions. The first question about the bounding rectangle, it's the hot water system. So I want to bound the sinks and the showers and the washing machines and the dishwashers. The toilets are generally not getting hot water, so I wouldn't bound them as part of the rectangle. Okay. Refrigerators tend to be within the rectangle, even though they only get cold water, but it's really about the hot water system. I hope that answers that question. And then I'll answer Tim's question, and then we'll go back to the one you've raised, Brett. That's okay.
Well, then let's just make sure, so people who can't see the question is approximately what was the cost of consulting and engineering to right size those 94 apartments?
It's a great question. This math normally needs to be done by the consulting engineer, but most consulting engineers, the MEPs, don't know the method yet. And so I usually charge out at about, depending on how complex the project is, somewhere between 1 and 2 days of my time. It takes me much less than that to do the design work typically, but it takes almost all of that to talk with the team and explain how everything works, because there's more than just right sizing that I provide. Remember all those pressure loss questions we had earlier where you have to pay attention to insert fittings? An awful lot of people are going to Pecs as a part of the design process, and some people are able to actually get permission to use 3/8 Pecs when they get inside the apartments. And when we get to 3/8 Pecs, we have to pay a lot of attention to the pressure loss that's going to occur when they're running flows in the buildings. And so much of what I spend my time on in that 1 to 2 days is explaining to the team how to make all of it work properly. Okay, so I hope that answers the question of costs. Because of the web and all that abilities we have now, I don't have to be in the room. I can work from California, wherever the project is, and I'm happy to work with teams to get them up to speed. My goal is to teach lots of people how to use the water demand calculator as soon as possible so others can take over from me to do this design work. The other piece of the puzzle is that I'm currently leading a national effort sponsored by IATMO to figure out how to extend the water demand calculator into the future. One of the pieces we're looking at is to create a software program which makes it easier for the design engineers to use it in big buildings. Right now, it's a little bit tedious. The expected goal is to have it done in about the same time it takes now to use the old method. And that means it will be in no marginal cost to do the design work except for learning a new tool, sort of like learning how to use Revit or other tools that the engineers already do. It's pretty straightforward. We're also looking at extending it to other occupancies other than single and multifamily, like hotel, motel, like special care facilities, hospitals, dormitories, all those sorts of things we're looking to extend it to. So now to your question, Brett, if you would repeat it again, because I think I've lost it.
Well, it's just following up on evaluations of hot versus cold water. And I was curious if you had said water savings with the Myetmo tool, but are those water savings really only looking at hot water?
Yes, they are, quite frankly. So right sizing has to do with flow rates, not consumption.
Right.
So if I have a toilet that needs 3 gallons or 4 gallons a minute to fill, I do not want to use 3/8 tubing for that. I want to use 1/2-inch tubing. Whether it's copper or Pecs, I really want to use the bigger diameter, okay, or CPVC. I don't want the noise, but I'm still going to fill the toilet and it's still going to flush a certain volume. Does that make sense? If I'm filling my dishwasher, it's going to fill a certain amount of water. US dishwashers want hot water, Europeans want cold water, but one way or the other, it's still going to use the same amount of water.
Right.
Does that all make sense?
Right.
Where we get the water savings on indoor plumbing, and the water demand calculator is currently only available for indoor water use.
Well, go ahead.
Yeah, that's what it's available for.
It sounds like, not to go too far off, but, talking about these lower flow, and we know that toilets are our #1 water users for the most part, unless you're getting into the irrigation side, which is a whole nother rabbit hole. But anyway, it sounds like, to be successful with the lower flow toilets, you really need to have a proper type of plumbing system, somewhat similar to what we're talking about here for hot water. Is that true?
Yeah, you need to make sure you've got the right, you want to be able to fill them in a reasonable amount of time without any noise in the plumbing. And then the most important question for toilets is how far will the drain lines carry? And it turns out that the single most important thing to pay attention to that we have control over is the slope of the drain line. The plumbing code allows us to do an 1/8 inch per foot minimum. Don't do it. Keep it to 1/4 inch. It works better. Particularly the big line that runs out of the house. Keep it at 1/4 inch. By the way, there's an effort underway to look at right sizing the drain lines for the same reason we're right sizing the supply lines. Right? If the water demand calculator only predicts 10 gallons a minute and the plumbing code predicts 80 gallons a minute of inlet water, why would you size your drains for 200 gallons per minute going out? Doesn't make any sense, right? You should match them so that because inses and gazoutas need to be better matched. So the water savings that we have identified come from less wait for hot water to arrive because we've cut the diameter of the pipe down by 1 or 2 sizes. That affects how long it takes for hot water to reach the fixtures, all other things being equal. And that's water savings we're accounting for. And so that's what we're accounting for water savings.
So, Pecs, my understanding is that's the direction we're headed to, cost. Right. And I don't know how inflation and shortages of materials have harmed copper versus Pecs, and maybe you can speak to that briefly. But we were well on our way to transitioning to Pecs. CPVC, I don't see it anywhere. Maybe it works somewhere, but and my understanding of Pecs is that it's supposed to, at least in theory, be more energy efficient as far as heat loss through it versus copper. So it sounded like from when I'm listening to you, it's these interior fittings. Maybe that's the problem with Pecs, or maybe you can explain a little bit more. So, what have you seen anyone try to make those fittings exterior? Could that be a solution, or just what are your general thoughts there?
There are exterior fittings for Pecs. They're called, one of the brands is called Shark Bite.
Mm-hmm.
They grip around the outside like those finger torture thingies that we used to get as kids, right? They grip your fingers, you won't let them move. It's the same idea for the Shark Bite type fittings. And the waterway is not affected that way. So those fittings tend to have pressure losses that are very similar to what you'd see in copper or CPVC, which is a big deal. The dilemma with those fittings is they're an outside clamp with an O-ring. And so the question I have for everybody is, how many years do you think those will last behind the walls? We have evidence that sweat copper construction will last 60 to 80 years easily before you have to worry about repairing it, all other things being equal. You can get pinhole leaks. You should always pick type L or larger wall because you want the time. You want to make sure your velocities are right so you're not unintentionally wearing out the copper pipe from the inside out. But all other things being equal, you want to keep the copper will last a long time. I see a related note coming through in the chat that Uponor makes fittings that require expansion of the Pecs to fit. And it does help combat the problem. That is absolutely correct. So I have recommendations that I answered online earlier, but I'll say them out loud now. If you're going to build a plumbing system, every twig has to have a beginning and an end. Something has to get the water on the branch pipe or the twig to it, and something has to take the water out of the twig to go to the fixture. Okay, so there's hot twigs and cold twigs. Each of them have to have a beginning and an end. Do not put elbows in between the beginning and the end. That's an extra fitting, particularly critical when you're down in small diameter pipe. Use bend supports if you need them for making sure the pipe stays where you want it to go. Okay, bend supports have an internal radius of curvature on the order of 6 to 8 times the nominal diameter of the pipe. Call it 10. If you can keep the internal radius of curvature of the bend to 10 times the nominal diameter or more, you will not have a problem with pressure loss through the change in direction of 90 degrees. When you have to have a T, put a T. If you can put 2 T's close together in a mini manifold, you have less pressure loss with 2 T's as a mini manifold than 2 separate T's. Minimize the number of fittings. Be clear about how you're going to manage that. The expansion fittings that Uponor makes have the least pressure drop of all the fittings I've measured. Uponor is not the only company that makes that type of fitting. There are 4 or 5 different product standards for each of the different fittings from a manufacturer's point of view, and all of the pressure losses that we've measured group around the fitting types. Having said all that, you have to plan for the pressure. So when I do design work, I work from the things that I know are the most lossy in pressure. And then you come back and tell me I want to use something that's not that, it's something that's got less pressure loss. I don't have to go back and rethink the entire design. It will continue to work well because everything I can do in reality has less loss than what I designed for. Now you're going to come back to me and say, I have a project that's really tight on pressure. I don't want to put in booster pumps. Really don't want to go to that expense and trouble. How do I manage that? And then we go back and we look at, well, if you pick these 3 things instead of those 4 things, you'll end up being much better off on pressure loss and your building will work right. We can refine it, but if we start with low pressure loss assumptions, we're going to have problems. We have to assume relatively high pressure loss on the way from A to B. Hot, cold, everything. It's all, we have to plan this properly. We've done it. I mean, this is not hard. I highly recommend that you all get together and do a workshop somewhere. You've got technical training colleges in the state. You've got some great capabilities. When we built our first project in upstate New York, I was given certain products that we had to work with. And guess what? They were some of the most pressure lossy ones that we could pick. How did I know? I went and measured them. That's why I did the experiment. So what we did before we actually built the first project is when we came back with a 1.25-inch main for that 35 unit apartment building. Well, when the day I did the research, I ended at the end of the day with all the math, and I went and had a good stiff drink. Thought about it all night, got up the next morning, rechecked all my math, had another drink, then called my partners and said, we need to do a mock-up. So my friend Pete in upstate New York went to his workshop, got all the pipe we needed for the long run of plumbing. We set it up so that the apartment at the end of the run was getting the maximum amount of water estimated by the water demand calculator, which was almost 4 gallons a minute. Remember, we've never measured more than 5 gallons or 6 gallons per minute in an entire 35 unit apartment building, right next door to the one we were building, right? Same occupancy. So we were measuring it at almost 4 gallons a minute. We keep 4 gallons a minute going on the branch to that apartment. And then we open up taps around the rest of the big main line, and we keep the water going as fast as we can coming out of the apartment, 3.5 gallons a minute. And we watch what happens to available pressure as we raise the flow rate on the main line. Guess what? Our predictions in design matched what we measured in the mock-up. And my recommendation to everybody is to start building a few mock-ups of some potentially problematic designs so you get comfortable with how they actually work. I don't just do design. I go out and I measure stuff so I can see if what I think about in design is actually working in practice. And the fastest way to get everybody past up this learning curve is to do some of those practical measurements. If you want to talk about how to set up workshops like that, we can do that, Brett. It's a lot of fun. You know, people actually do like to get wet periodically. It's easier in the summer than the winter, but we can do this any time of year you want.
Yeah, we'll have to take you up on it. I mean, there's definitely a need for training our plumbing contractors for the next high performance home. You know, we need training not only on the heat pump water heater expansion and now rebates that are coming down the line, but you know, also on the proper right sizing of the plumbing. So I think it makes a lot of sense to think that through, and hopefully other folks listening in too can think about it and reach out too. So we are, you know, on that note at the end of our time here for the session, Gary. So where can people go to contact you or learn more or reach out if they want to?
I think it's on the presentation at the front page. So let's just use that. You can send it out to everybody or paste it in the chat. Either way works. I have one more point related to this, the heat pump water heaters that are coming. I highly recommend to everybody to watch the presentation from the Northwest Energy Efficiency Alliance called The Amazing Shrinking Room. I think that's its title, where they talked about taking the 700 cubic feet of volume required by the manufacturers of standard 240 volt heat pump water heaters, and they kept shrinking the size of the space. And they came up with some really interesting conclusions and recommendations about if you have to put heat pump water heaters in smaller than 700 cubic feet, how to make sure they work pretty darn well with high COPs as you do that. So I think that we ought to do, I would recommend having a class just on that topic alone, perhaps by the folks from NIA, would be a great addition to your collection, because they're continuing the research and it's very valuable as we move forward in this electrification effort.
Yeah.
All right,
yeah,
enough. We're good.
Thanks for that note. Thanks for that point. We'll look into it. So, Gary Klein, it was good to have you back and good to virtually see you out there. And thanks everyone for joining us. For those of you in the US, have a wonderful holiday and take care, everyone. Thanks.
Bye, everybody. Thank you.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.